When you're building something really complex, intellectually complex, I mean, maybe like a legal system or even a bridge, right? That foundation, it just has to be rock solid.
Absolutely. And in mathematics, our foundation, well, it's built on axioms. These are the sort of agreed upon rules, the starting points that we don't prove. They're like the trunk of the whole mathematical tree.
Okay, so if the axioms are the trunk, how do we make sure, I mean, really make sure, that a super complex proof, maybe hundreds of pages long, actually connects back properly, that the theorem is, solidly on that trunk?
Yeah, that's a fundamental challenge. It really is. And we know, unfortunately, that human checking peer review isn't foolproof.
Right.
Just look at the four-color theorem. There was that proof back in 1879. Everyone thought it was fine for, what, 11 years?
Uh-huh. And then, oops, a fatal flaw was found.
Mhm.
And today's proofs, they're orders of magnitude more complicated. We really needed something else.
Something more reliable than just human eyes, however expert. So this problem of trust,
Mhm.
how does this new tech help fix that? Well, the answer that's emerging is the proof assistant, or PA. The mathematician Kevin Buzzard has this great analogy.
Oh, yeah.
He says a PA is like a really pedantic student, the one always asking, but why is that true? Explain that step.
Huh, okay. Constantly demanding justification.
Exactly. The software basically forces you, step by step, to formalize the entire proof in a specific computer language. And the key thing is, the proof simply won't run, it won't verify, unless every single tiny logical step checks out mathematically. No gaps allowed.
Okay, that sounds incredibly rigorous.
Mhm.
Before we get into how that's changing, like the whole culture of math, just a quick word. This deep dive is sponsored by Embersilk. If you need AI education or integration solutions, check out embersilk.com.
So what's really fascinating and maybe a bit unexpected is that these PAs, these very rigorous tools for individuals, they're actually sparking huge collaborations.
Right, because math has this reputation, doesn't it? The
Yeah.
solitary genius working alone.
It does. But formalizing these proofs is just so complex, so demanding, that it almost requires a team effort. It's becoming much more like, say, open source software development, a community project.
And we're seeing results from that teamwork.
Definitely. Look at the polynomial Freiman-Russa conjecture. It's a result in combinatorics, quite abstract. The original paper was 33 pages,
Okay.
a group of about 30 people, and it was a real mix. Mathematicians, coders, even puzzle fans. They formalized the entire proof in the lean proof assistant. And they did it in about 3 weeks.
Wow, 3 weeks for a 33-page proof. That's incredible speed through collaboration. How does that work structurally?
It works because of something called the dependency graph.
Yeah.
Lean, the system they use, it basically forces you to map out the proof's skeleton. Definitions are like rectangles, theorems are maybe ellipses,
Okay.
and arrows connect them, showing exactly what depends on what. As people formalize different parts, those bits of the graph, they turn the satisfying dark green color.
Ah, so it's visual progress. And modular.
Exactly, modular, that's the key. It means for huge projects, like people are doing now with Fermat's last theorem, you can specialize. If your expertise is, say, real analysis, you can focus just on formalizing that section. You don't need to master every single detail of the entire proof structure yourself.
That makes sense. It allows specialization within this massive collaborative effort.
Precisely. And this kind of structural certainty, this absolute rigor, is why the connection to AI is suddenly becoming so important.
Right. This is where it gets really interesting, I think. The intersection with AI, specifically large language models, LLMs, we saw them hit that gold medal level at the Math Olympiad in 2025. Huge potential there.
Immense potential, yes, but also a significant risk, especially for research-level math. The big problem right now is what they call hallucination.
Where the AI makes things up.
Kind of. When an LLM gets stuck on a proof, unlike a human who might just say, I don't know, the AI's tendency is to sort of, well, lie or smudge the details to keep the output flowing. It wants to sound coherent, even if it's wrong.
That sounds dangerous for actual mathematical discovery.
Yeah.
You can't have smudged proofs.
Absolutely not. Which brings us back to Kevin Buzzard's idea. He's basically betting that the solution is to force the LLMs to output their proofs in a formal PA language first, like lean.
Ah. So the proof assistant acts as a filter.
Exactly. The PA won't accept smudges or logical gaps. It forces the LLM's output to be mathematically sound before it gets translated back into human-readable math. It checks the work, rigorously.
So it enforces honesty, essentially.
You can put it that way, yes. It's a verification layer. And that step, that formal verification, seems essential if we want LLMs to safely push the boundaries of research mathematics. It's all moving towards David Hilbert's old dream, really.
Hilbert's dream of formalizing all of mathematics,
Yeah.
making it completely certain.
That's the grand vision, yeah. Complete, verifiable certainty.
So what's the takeaway for us then? It sounds like proof formalization isn't just some academic niche anymore.
Not at all. It's a really active field. You had Fields medalists, top mathematicians, deeply involved at the recent Big Proof conference in 2025. It shows the quest for certainty is, well, very much alive and kicking.
And maybe even accelerating with these new tools.
And think about this. As AI models get trained on these perfectly formalized, verified mathematical datasets data with zero errors, zero smudges, what might they discover?
What do you mean?
Well, could an AI analyzing this vast structure of formalized proof spot something subtle, maybe a tiny inconsistency in our foundational axioms, something humans have missed for centuries? Could it reveal a whole missing branch on our tree of mathematics?
Wow. That's definitely a provocative thought to end on. A potential AI-driven revolution in foundational math itself.
It's a possibility these tools open up.
Well, that's all we have time for in this deep dive. If you found this exploration of mathematical certainty interesting, please do subscribe to the podcast and maybe leave us a 5-star review. It genuinely helps us keep these conversations going. Thanks for listening.